everybody. Welcome to the centripetal force practice problems, and make sure you're on the note-taking side because the centripetal force practice problems has slightly different numbers, and you're going to do those for homework. So on number one, it says a 100-gram ball. Well, first of all, you can't use 100 grams in a formula, so we got to change that mass to 0.1 kilograms by dividing by 1,000. Is swung on a 40 centimeter string, excuse me. Well, you can't use centimeters either, so we're going to change that to meters, 0.4 meters. And it's going 1.2 revolutions per second. Well, that's actually your frequency, and we need to change that to linear speed. So I'm going to put down revolutions per second here. And it says, what is the ball's centripetal acceleration? Well, the new formula you're going to use for centripetal acceleration is actually pretty easy. It's v squared over r. But that's linear velocity. And so what I need to do is I need to change this revolutions per second to regular velocity. And in order to do that, I'm just going to do it over here in different color. And so let's do this in green. We're going to take 1.2 revolutions per second. A revolution is the same as the circle, and since I want regular velocity, that's distance over time, the distance around a regular circle is its circumference. Well, the circumference is 2 pi times the radius, and the radius is given to you right here at 0.4 meters. So instead of r, I'm going to put in a 0.4 meters there. And then that's per revolution. So the revolution is going to cancel out, and I'm going to be left with 3.015 meters per second. Well, you take that answer and you're going to put it in for that v. So we come back over here, and so I say centripetal acceleration is 3.015 meters per second, and square that whole number, divide it by the 0.4, which is the radius, and that ends up giving you a total of 22.7 meters per second squared, which is once again regular acceleration. Now, if I want to find the ball's force, what you then do is we simply take mass times acceleration. So if force equals mass times acceleration, now on the homework problems out of the conceptual book, just use this equation, mv squared over r. You're probably saying, well, where the heck did you get that? Well, the v squared over r is this formula up here. I just shoved it in for a, okay? So since we already did the v squared over r, I can take my m is 0.1, times the answer I got of 22.7 meters per second squared, and that ends up giving you 2.27 kilogram meters per second squared. And that's the same thing as 2.27 newtons. And since force is measured in newtons, that makes sense. Now, what direction is centripetal acceleration? Well, if you remember, when I took the water outside in the hallway and we flipped around, the centripetal acceleration always acted towards the middle. So the centripetal force is towards the middle, and centripetal acceleration is towards the middle. So you could say toward middle or towards the center is a better way to say it. Just towards the center. On number 4, it says for you to draw a path on problem number 1, draw and label the velocity vector. Well, if you remember when I swung the rubber stopper around in the classroom, the rubber stopper wanted to go out tangent. So this is your velocity vector right here. That's what we call the tangent to the circle. And once again, the acceleration vector goes inward towards the middle like that headline. So let's draw a circular path for ball number 1 and draw and label the velocity. I just did that when it was number 4, so number 4 is actually here. This is number 4. Okay. Number 5. Uh-oh, sorry about that. Number 5 says, what is the minimum speed of a 0.2 kilogram ball? So I got a mass of 0.2. A 40 centimeter string, so that's 0.4 meters, can have to maintain a circular path of the arc. Now, if you think about a rubber stopper going around in a circle like this, if it was going the slowest it possibly could, and this was a string right here, okay? When it was going the slowest it possibly could and still go around the circle, there would be no tension at the top of that circle. And so what I'm going to do is this. I'm going to have the centripetal force that makes it go around in the circle. That's going to be the sum of all the forces. So there are two forces that make that go around in a circle. There's the force of tension on the string, and there's the force of gravity that pulls that rubber stopper down at the very, very top. Well, it wants to know what is the minimum velocity. Well, none of these have velocity in it, so you got to substitute. So I'm going to put mv squared over r. That goes in for the centripetal force. The tension, like I just said, if it's going around as slow as it possibly can up here, that means the tension would be 0 at the very, very top. And the force of gravity, like we did last chapter, was m times g. Well, what's sort of sweet about this is that your m's cancel out. And so if I want to find out what v is, let's multiply both sides by r. So now I'm going to have v squared equals r times g, because 0 goes away. I multiply both sides by r. And now you got to get the v by itself by taking the square root of both sides. So v equals the square root of r times g. And we can use this not just for a string, but we can use this for roller coasters that are going around in a loop. It makes no difference what the mass of that roller coaster is. It's all about the radius of the roller coaster. And so if the radius of the roller coaster is, of this string rather, is 0.4, and the gravity is 9.8, that means that that string must be going around at somewhere in the general vicinity of 1.97 meters per second, just to barely get around. Well, if I compare this to a roller coaster, and when a roller coaster goes around a loop, you would say, well, the speed determines on how many people are on the roller coaster. Well, no, it doesn't, because there's no mass in that equation. And when you look at a roller coaster loop, they often make it not in a circle. They make it longer in radius up here. And that's so that people actually go faster and feel more centripetal force. So that's why they sort of pinch the loop. It's called a cathoid loop. And it makes the roller coaster feel safer to the riders because there's more centripetal force. Part B says if the speed was doubled at the bottom, what's the tension on the string? Well, now I can't get the m's to cancel out because I'm looking for tension. So I'm just going to bring down the blue here. So I'm going to use the same equation of mv squared over r equals, the force of tension is what I'm looking for, plus mg. So let's just plug in all our numbers. So I'm going to have 0.2 times the velocity. Well, you got to remember it said that the velocity doubled. So I'm going to have 2 times 1.97. And I have to square that velocity and divide that by 0.4, which is the radius. That equals the force of tension, which is what I'm looking for, plus the mass, which is 0.2, times gravity. And you've got to make gravity negative 9.8 because it's pulling down. When you subtract the negative 9.8 from both sides times the 2, you're going to get a force of tension now, which ends up equaling 9.7 newtons. 9.7 newtons. Now we're going to number 6. You got this car going around a curve on a flat road of 40 meters. So once again, the mass of the car is going to be 2,000. The radius now is 40 meters, so it's a very, very large turn. So now you're a civil engineer, and you got to figure out whether a car that's going 40 miles per hour, well, as soon as I know that my velocity is 40 miles an hour, I know I got to change that. So I'm going to go ahead and cancel that out. Since the miles, I know that there's 1,609 meters in 1 mile. And I also know that there is 3,600 seconds in 1 hour. And so that means that that car is actually going somewhere around 17.8 meters per second. What I want to figure out is this. If the car is going 17.8 meters per second, will it stay on the pavement? Is it going too fast to make the turn if the coefficient of friction is 0.65? Well, let's talk about that. What holds the car on the road is friction. If it's going around a turn, that means I can make two things equal each other. the centripetal force has to equal the friction force, or it's not going to stay on the road. So I'm going to now plug in the formulas for these things. Well, centripetal force is mv squared over r. The friction force, if you remember, friction is fun. So that's mu times the normal force. Well, since this, if you remember normal force was the same thing as the weight. So I'm going to scratch out that Fn right there and make it mu times m times g. So once again, that friction force equaled mu times normal force, and I simply put in the mg for the normal force. So what's sweet about this, once again, is the masses cancel out. So let's see if this car is going to make the turn. If I want to find out v all by itself, I'm going to multiply both sides by r. So now I got v squared equals rug. Remember the square root of 2 Doug? Well, to figure out whether a car is going to go around a turn or not, now we're going to take the square root of both sides, and we're going to say that the velocity to go around the turn is the square root of rug. So let's plug in our numbers. So r was 40 meters. Mu, which was the coefficient of friction, is 0.65. G is 9.8. And so that means my velocity that I have to be going, the maximum velocity I could be going and stay on that road is 15.9. That's the maximum velocity. That's the highest you can go and still stay on the road and have friction to hold you on there. Well, let's look at how fast the car was going. The car was going 17.8. This is faster than the maximum velocity due to friction, so the car skids off the road. All right. And number 7 is when you get into like coming off an expressway and you have a banked off-ramp. It says, what component of the normal force provides the centripetal acceleration of the car around a turn? So I want you to picture this ramp right here, but the car is not going up or down the ramp. It's actually coming out of your computer screen. So in other words, this would be the wheel of a car, that would be the wheel of a car, and this is the front of the car, and here would be the bumper, this would be the windshield, and you're actually looking at the driver, and the car's coming out of the road. It's not going down, it's not going up, it's coming out of the road. Well, if you think about it, the road has to do 2 things. It has to push up. I'm going to draw this line again. Okay? So I'm just going to draw that same diagonal line going down like this. Okay? The road has to push up against gravity, but it also has to push horizontally towards the center of the circle. So I want you to think of this off-ramp coming out of the board and going around in a circle and then coming back in over here, okay? So it's sort of hard to picture this as much as you can, but the road has to push diagonally according to that blue line, just like that. Well, that blue line is divided up into 2 things. That blue line is actually the normal force because it's perpendicular, even though it doesn't look like it. I drew that really, really poorly. Let me draw this again. So that blue line should be perpendicular to this black line, like this, okay? And the normal force then is divided into a force that goes straight up against gravity. So I could say that that red line is the force of gravity, just in the opposite direction. And then this green line is actually the centripetal force because it pushes the car towards the middle of the circle that it's going in. So the normal force, the component of the normal force, if this is normal force, is the blue one, the component of the normal force is always the horizontal one. And that's what pushes you towards the center of the road, the horizontal component. It's so hard to do online where you can't actually see what I'm doing here. So in number 8, it says calculate the centripetal acceleration and velocity of a Daytona race car going around a curve that's banked at 20 degrees with a 316 meter radius. So now I have this here at 20 degrees, and I have a radius of 316. And let's talk about this first. Well, if I want to know the centripetal acceleration, I first of all got to know the velocity and the radius. Okay, but let's start off with centripetal force, because I know that these components are making a centripetal force. So let's look at this. I'm saying centripetal force equals, well, let's look back up here at this number 7's diagram. If that is a 20-degree angle, right up here, this is a 20-degree angle. Once again, that road has to push the car up. Whoops. The normal force goes like this. Okay, so that means the normal force would also come down. Oops. Oh, sorry about that. Can't get this to erase. That stinks. Still can't get it to erase. All right. I'm feeling my chalkboard's locking up. And then the centripetal force is going to push this way, and my chalkboard just locked up. That stinks. I'm going to have to make the movie stop right here, and I will come back with another video that starts with number 8 because the smartboard just locked up. Sorry about that. Okay, everybody, I'm going to save the video here. So let's just say my car is sitting right here. Okay. Once again, this is going to be a 20-degree angle. I want you to look at what's happening here. That car has gravity that pushes straight down like this, correct? And that means the road has to push straight up like this. Just follow me what's going on here. The road, though, actually pushes at a normal force. In other words, not only does it push up, but it pushes sideways. And so it's actually going to push at the normal force is going to come up like this. So therefore, that's a 90-degree angle there. Okay. And so I want you to just follow that line straight back. Just go with me here. And then that means that the centripetal force is going to be pushing this way. Now, you have to follow me. If that is a 20-degree angle down here in the lower right-hand corner, and that black line makes a right angle with the blue line, that means that this angle right here must be a 70-degree angle. Okay? That must be a 70. Well, I want you to follow the green line up. Okay? If the green line going down is, the black line, follow the black line, here's the black line, it makes a right angle with the blue line. Well, if that's a 70-degree angle, then that means this must be a 20-degree angle. Let's see and follow that. Remember, the black line makes a right angle with the blue line. So if the 70-degree angle with the black and the green, to finish out the 90-degree angle, makes it make a 20. Well, since you have opposite interior angles, that means that this angle must be 20. Gosh, I know it's hard to read there. That's 20. So let's figure out what we're trying to find here, right? If I want to know the centripetal force, I know two different sides here. The centripetal force is going to be the opposite side. See that red side? Well, I know the green side because the green side is gravity. Force of gravity is the green side. And the way you find the green side is by simply taking the sorry about that, the computer's locking up. The mass times gravity is going to be the green side, and I want to find the opposite side. Well, think about what you have here. You're having the adjacent side, which is green. Okay, so here we go. Watch this. I'll do this on the board here. The adjacent side is green, and that's mass times gravity, right? That's the adjacent side. Okay, well, let me just put A in there for adjacent. That's A. The opposite side is the red side. And so what trig function are we going to use? We're going to end up using the tangent. So we'll just put tangent in here. So if I want to find the opposite side to get the centripetal force, we are going to take the tangent of 20 degrees times the mass times gravity, or the adjacent side, and that's going to give me the centripetal force. Well, hopefully in your head right now you're saying, well, wait a minute, they didn't give me mass times gravity. Well, if they don't give you something, you got to plug in some formulas. So what's the formula for centripetal force? It's m times v squared over r. That equals tangent of 20 times mass times gravity. Well, that's great, because now the masses cancel out. So that mass is going to go away, that mass is going to go away. And so if I want to find out the centripetal acceleration, which is v squared over r, it's the same thing, I'm just going to take the tangent of 20 times 9.8. So since this is v squared over r, everybody see that right there? That is the same thing as centripetal acceleration. The tangent of 20 times 9.8 ends up giving you 3.56 meters per second squared. Now it also asks you to find the velocity. Well, you know the acceleration, finding the velocity is pretty easy, because since acceleration equals velocity squared over r, we now simply put in all these things and solve for it. So the acceleration is 3.56 equals v squared over the radius, which is 316. When you multiply both sides by 316 and take the square root, you end up getting a velocity of 33.5 meters per second. And once again, if you want to know how I did that, I took 316 times 3.56. That got rid of this part right here. You had to multiply both sides by 316. And multiply both sides by 316. And then I square rooted that to get the v all by itself. Now finally we're going to go down to number 9. I'm not going to do 10 because it's too long to put on the video. I'll do that in class for the AP kids. On number 9 we have this Gravitron carnival ride, and I'm going to show you a movie of it in class. But basically, here is a wall, and you are standing up against the wall, and it starts going around in a circle, and you feel it push you out against that wall. And then the floor drops out, and you're just sort of pinned up against the wall, hovering there. Well, you're really not getting pushed out. The centripetal force is actually pushing you towards the center like this. And what it wants to know is this. Part B, what is the speed of the rider? Well, first of all, it says the Gravitron carnival ride has a radius of 2 meters. So I'm going to put down r equals 2. Okay. And it spins the rider once each 0.9 seconds. So the frequency is 1 revolution every 0.9 seconds. So we got to figure out what that is. And we're going to do that in meters per second here, since we're doing linear velocity. Well, a revolution, we got to get those to cancel out first. A revolution is the same thing as the distance around a circle, which is what we call circumference. So I'm going to put 2 pi r, but instead of r, I'm going to put in a 2, because 2 is your radius. Okay, so it's the same as 2 pi r. Then what I'm going to do is multiply that all out. And when you do that, you get 13.9 meters per second. So that is actually my velocity now. Just change frequency into velocity. Part B asks you to find out what is the centripetal acceleration. Well, the centripetal acceleration is v squared over r. So I'll simply take my answer of 13.9 squared, divide it by r, which is 2 meters. And so that gives me 97.5 meters per second. That's a heck of an acceleration. Squared, rather. Meters per second squared. Now, finally, it says, what is the coefficient of friction needed to keep the rider from slipping? Well, this gets tricky. Let's go back to a couple chapters ago when we said that the coefficient of friction is the friction force divided by the normal force. Now, I might have to repeat this in class because you've got to sort of see what I'm doing here. Now, I want you to look over here at this black rider. Okay, the black diagram with the rider on that. The friction force actually keeps the rider from going downward. So the friction against the wall keeps the rider from going like this. So that means that the friction must be equal to the person's weight. Well, if you remember, weight was mass times gravity. Now, normal force, you think, well, normal force always acts perpendicular to the surface. Well, think about it. Perpendicular to the surface, and surface is going straight up like that black wall. Well, perpendicular is going to be this red line here. What did we call that? We called that the centripetal force. So we can now say that the normal force is the same thing as the centripetal force. And if you spread that out even more, you can say, well, that means mg divided by the centripetal force is mb squared divided by r. Well, what happens to the m's? The m's cancel out, so it makes no difference how heavy you are. So if you want to find the coefficient of friction, you simply take your gravity, 9.8, divided by the b squared, which we got over here of 13.9. Square that little slap mammy, and divide all of that by r again, which ends up being 2. And let's make sure all that's in parentheses. And so your coefficient of friction ends up being 0.101, which is very, very, very slippery. So I don't even care if you're wearing parachute pants, you can pretty well stay up on that ride. Okay? Let's get AP. I'll do one like number 10 in class. So on the AP problems, if you get to one like that, don't worry about it. We'll just get to that in class. Okay? Hope you have a great day. Sorry about such a long video. Bye.